Now, this is the third axiom, and it states that if A and B are two disjoint events, which means A intersection B equals to phi, then the probability of either of these two events equals to the sum of the separate probabilities. To understand this axiom properly and to know how does it work, we have to recall something from our sets lecture where we studied disjoint sets. Okay, so when two sets have no common elements, the two sets are called disjoint sets. Similarly, when two events have no outcome in common, then the two events are called disjoint events. Okay, so let's see an example and then we will be getting back to this axiom and proving it. So the example involves a problem. So let's roll a die. The question is, what is the probability of getting an even number or a multiple of 5? Okay, so this is the question. To solve this problem, we have to define the events properly. So let's say event A equals to getting an even number and B equals to getting a multiple of 5. All right, so now what will be the elements or the outcomes in event A? We know that there are 6 outcomes possible, that are 1 2 3 4 5 6, and only 3 even numbers are there. They're 2 4 and 6. So A will consist of these 3 elements and the cardinality of A will be 3. Similarly, similarly, the event B will have only one element in it, and that is 5 itself, because there are no other 5's multiple in the numbers 1 through 6. So yeah, B will have only 5 in it, and the cardinality of B equals to 1. Okay, 1. All right, and let's determine the sample space. So the sample space will have these 6 elements and the cardinality is 6. It's simple. We have solved similar problems before. Now we have to determine the probability of either getting an even number or a multiple of 5. So either A or B. So we know that union stands for or. So P of A union B has to be determined. Instead of using this formula now, oh, by the way, one thing to notice, and that is, see A and B, these two sets or these two events have no common elements, right? That is why we can call that A and B are disjoint. Mathematically, we can write A intersection B equals to phi, which means cardinality of A intersection B equals to 0. This is going to be a useful information for later. So anyway, we have to determine P of A union B, and I hope you have understood what disjoint events are. So yeah, P of A union B. Now, instead of using the formula here, we are going to prove this formula using the principle of inclusion and exclusion. You have studied it in your first lecture, so I hope you recall. So the principle states that cardinality of A union B equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. All right, since these two events are disjoint, so we know that A intersection B equals to ORI, so it has no element in it, so intersection B is cardinality equals to 0, so we can write it like this. So finally we can deduct from this line, yeah, and now we are going to divide this equation by the number of elements of the sample space. Why are we doing this? Because we need to convert this formula into a probability formula. Okay, so by the definition we can say that it's probability of A union B, either A or B, and it's probability of A and it's probability B. Yeah, we have reached our conclusion that this axiom is true, right? Now we are going to put the values of P of A and P of B in this equation to determine P of A union B. Now we have modulus A, we have modulus sample space, so 3 by 6 it's half. Again, P of B will be simple, 1 by 6. Okay, so now putting these values in this equation, we get, finally we are there. So it's 4 by 6, which can be reduced to 2 by 3. Yeah, that's it. So this is the answer of this problem. I hope you understand it. You see the figure 1, and it's the Venn diagram representation of our axiom 3, where A and B are representing two disjoint events. These two events are disjoint, that's why there is no common element in between these two events. So there's no overlapping, so they satisfy the axiom 3. Now look at figure 2, where A is an event denoted by the yellow circle, and the rectangle again is representing the sample space. So it covers all the outcomes possible from an experiment. Okay, so what is AC here? A prime AC. What is AC? From our idea of set, we know that AC is universal set minus A. Okay, so from the perspective of events, we can say that if A is some event happening, then AC represents the event of that event not happening. So A is something happening, AC means that's not happening. Okay, so my question to you is there any common outcome that both of A and AC share? No, there's none, because there's no common element or no common space in between these two sets or events. Therefore, we can say that A and AC are disjoint. Okay, basically the yellow circle is representing event A, and the region outside yellow circle and inside the rectangle, which is pink in color, is AC. So there's nothing common in between these two events. That's why we can say that P of A plus P of AC, using axiom 3 way I'm writing it, union AC. Okay, now P of A plus P of AC equals, look at the figure, this is A, this is AC, so the union of these two events actually covers the whole sample space. So here the A union AC can be replaced by omega, right? Since it covers the whole sample space, the A union AC can be replaced by this. So now from our axiom 2, we saw that P of omega equals to 1, therefore it's 1. That means P of any event happening plus P of that event not happening equals to 1. This is very important, and we are going to use this corollary in solving some difficult problems in future. So remember this. So probability of some event A happening plus probability of that event not happening equals to 1. Alright? Here's another problem. In this problem, the statement is, suppose we pick a random letter from the word Tennessee. Yeah, so it's a 9-letter word. There's some repetition of letters here. So the question 1 is, what is the sample space? All right, so to solve this problem, we have to determine the sample space. The experiment here is to pick a random letter, right? That's the experiment. So the sample space will cover, let's say it's omega. So the sample space will cover all the possible ways to choose a letter from this 9-letter word. All right, so I can write it like the first letter. That means I can choose the first letter or the second letter or the third or fourth. So thus I can choose 9th letter. Okay, any of these 9 letters can be chosen, or I could write it like T and then E, then N, then N, then E, S, S, E, E. You can tell me that we are not supposed to repeat the same element in a set. So why am I writing E multiple times or N multiple times? The answer is we are actually not writing the letters, sorry, we are actually enlisting in how many ways we can pick a letter from this 9-letter word. So we can pick the T or we can pick the first E. That's why we can write it like E1, then N1, N2. This is E sub 2, S1, sorry, yeah, S2 and E3, E4, right? So if we choose this, that means I can pick the first E. If we choose this, then that means I chose the second E. All right, but if we put the letters like this, suppose T, E, N, S, it wouldn't be clear which one of these 4 E is being picked, right? So the number of ways is not supposed to be 4. So it's wrong. So the sample space looks like this or this, and the cardinality of the sample space will be 9. I hope you understand this. So the second problem, this was the first part. The second part, the question is, what is the probability of choosing an E? What is the probability of choosing an E? Now the event that I'm interested in is asking for choosing an E. So let's name this event E, and it will have 4 elements in it: E1, E2, E3, and E4. See, if we wrote TENS, the event will have only 1 element in it, and then the final probability would be 1/4, which is erroneous. All right, so the event E, where we can choose any of these 4 E's in the word. So there are 4 ways to pick one E. And now the cardinality of event E is 4. Then the cardinality of the sample space is 9, that we have determined in the previous part. So the probability of E, or probability of choosing an E, is equals to 9/4. All right, so this was a tricky problem. I hope you understand it. The part 3, what is the probability of choosing either an S or an N? So now again we have encountered an either or problem. So let's define the events first. Let's say S is the event of choosing an S, okay, and N is the event of choosing an N. So either an S or an N. So we have to determine the probability of S union N. Union stands for or. So yeah, now see what are the elements in S. There are 2 S in the sample space, right? S1 and S2. So S will have S1 and S2 in it. So cardinality of S equals to 2. Again, there are 2 N in it. So in set N, there will be N1 and N2, 2 elements. Its cardinality is also 2. And note that there is no common element in between these 2 sets. So these 2 sets are disjoint sets. So we can use our third axiom that states that P of S union N for 2 disjoint events S and N will be P of S plus P of N, right? So now, what is P of S? This is, and this is, yeah, and now we are putting the values here. So 2/9 plus 2/9, which is 4/9. So this is the answer. I hope you understand it. Now we are going to solve another problem, and through the solution of this problem we are going to conclude a formula regarding the independence of events. So the statement of the problem is: roll two dice, find the probability that both of the numbers appeared are greater than 3. So you are going to roll these two dice, suppose it's d1 and it's d2. So after rolling them, two numbers will show up and you have to find the probability that both of the numbers are greater than 3. Okay, so we have solved a similar problem before. That is why we have made this sample space chart where all of the possible results are plotted. You see there are 36 cells here, 1 1 1 2 1 3 1 4. All of them are the possible results. So our sample space is here and the modulus of sample space is 36. Now we need the event to be declared carefully. So let's say our expected event is E and it is the event of getting greater than 3 from both the dice. Okay, so our job is to determine the cardinality of E. So in how many ordered pairs here both the elements are greater than 3? If you look at it carefully, then you will see that this 3 by 3 square with 9 ordered pairs are satisfying. Sorry, there is a typo. It should be 5 here. Yeah, so this 3 by 3 square has 9 cells in it and all of the ordered pairs satisfy the condition given in the question. So there are 9 ordered pairs satisfying, so cardinality of E equals to 9 and cardinality of sample space is 36. Therefore the probability of E equals to 9 by 36, which is 1 by 4. So this seems pretty much simple while we have already created this chart. But my question is, if there were 3 dice instead of 2 and you were supposed to find the probability for all of the numbers appeared to be greater than 3, then how would you do it? Would you try to solve the problem that involves a grid of 216 cells in it and then keep searching for the ordered pairs that satisfy the condition for this question? No, that would kill a lot of time and it's not the easier way to solve this problem. So let's try to solve the same problem we just have solved in a relatively easier manner and then get back to our problem with 3 dice in it. Okay, so to solve this problem again, we are going to have 2 boxes. Suppose this is box 1, it's box 2. So you have to put the result from die 1 here. I'm sorry for the noise. So you have to put the result from die 1 here in the first box and the result from die 2 in the second box. So you know that there are 6 options to fill up box 1. Similarly, 6 options for this too. So now the total number of ways you can fill up both these boxes is 6 times 6. We have already talked about it in a previous example. So what we are interested in now, this is the total number of results, but we are interested in filling up both these boxes with numbers greater than 3. Alright, so if you want to put numbers greater than 3 in this box, only 4, 5 and 6, these 3 options are available. So I can say that 3 options for box 1 in my expected event, of course. Similarly, 3 options for box 2. Okay, so 3 here, 3 options here, so total 3 times 3 equals to 9 ordered pairs will be there, or total 9 outcomes are in the sample space that satisfy the condition in the question that both of the numbers are greater than 3. Alright, So now we are almost done. By the definition of probability of an event we are interested in, the probability is number of favorable cases by number of total cases. All right, or you already know that this 9 is actually the cardinality of E and this 36 is cardinality of omega, so equals to 9 by 36, which is 1 by 4. So why did you solve this problem in the second method? Because it's relatively easier and it gives us an insight to solve a problem that involves higher number of dice or higher number of variables in it. Okay, so now let's get back to our problem with 3 dice. So if you roll 3 dice, then you will have 3 boxes to fill up, 6 options for each. Okay, so 6 times 6 times 6 equals to 6 cube, which is 216. This is what we were talking about. I told you that 216 cells. So if we started to construct a table manually, then it would have 216 cells in it and 216 different triples, and then we would have to search for the elements that has all its 3 elements greater than 3. Okay, so it would be a lot harder. So now 216 is the number of elements in the sample space when rolling 3 dice. So it's 216, and similarly you are being similarly you have been asked to fill up all these boxes with numbers greater than 3, and those shouldn't exceed 6. So 3 options for first box, 3 for the second, and 3 for the last. So 3 times 3 times 3, which is 27. So there would be 27 triples in our expected event. Suppose it's E3, the subscript 3, it denotes we are rolling 3 dice. So anyway, so it's 27. So by the definition of probability, P of E3 will be 27 by 216. It's a lot easier, right? So I hope you understand.